Okay, so in this video, what we're going to do is start with Haberman's section 1.5. And essentially the goal of this section is to show that this heat equation, or how heat flows, essentially the same equation in higher dimensions. Okay, so the goal of the section will show that the heat equation holds for functions that may depend on multiple variables. Okay, either 2D, 3D, in general, however many dimensions you want. This is just another way of writing it where X bars kind of the vectorial version of it. And so what are we looking for? Well, we're looking for an expression of this form. Okay, where again, here, this was time derivative, the temperature. There shouldn't be a hat right here, right, because temperature is a scalar. But we're looking at the change in temperature and time, right? These are properties of the material. And what we would like to have is some expression that says, right, well, we have some source term again, and we have something that looks like the x derivative of this, right? So again, something that depends on the temperature and the gradient in temperature, okay? So the issue about expecting something exactly like this is that, right, these functions depend on multiple variables. So, right, we can't just be taking a derivative with respect to x or with respect to one of them. We'll have to incorporate kind of the flow or the gradient in multiple dimensions. And that's the goal of this section. Okay. So question is, well, how does heat flow in 2 and 3 dimensions? Okay. So some notation, if U is going to be a temperature of space and time, okay? And so throughout this derivation, we'll assume that space is 3-dimensional. So if U depends on space and time, then in the end, this is what the heat equation is going to look like. Okay. If we write out kind of the names of some of these operators, this is going to be the divergence of K0 times the gradient of U. Okay. So this divergence, this is kind of so the divergence of a vector field is the dot product of kind of the gradient with your vector field. There's another video that reviews some of these tools and techniques from multivariable calc. But this is our end goal right here. Okay? And so in a sense, this piece right here plays the role of an x derivative. This piece right here plays the role of kind of that other x derivative. But otherwise, all the pieces are still more or less the same. Okay? And so, right, so specific heat, mass density, and this kind of, I don't know, diffusion coefficient, those all depend on the material, okay? So in the event that C rho and K0 are all constant, well, this expression simplifies a bit, right? Move C rho, kind of divide through, move this K0 out in front. You get something of this form, right? So this constant K is K0 divided by C times rho. Another way we can write this is K times kind of nabla squared of U. And another way we can write this is K times delta U, or this is usually called the Laplacian. Okay. We won't use this notation much because we like to have these delta x as small increments, so we don't want to confuse this for small increments. But these are all kind of equivalent pieces of notation for kind of this operator. Okay. Generally, we'll write this kind of, I guess, in one of these two ways. Okay. This is what we're actually doing. This is notation for the same thing. Okay. And so, right, what's another representation of this? Well, if you write out what the divergence of the gradient is, you end up with this expression, okay? Just take the second derivative of your function with respect to each of the variables, each of the space variables, add them up. That's kind of how this that's how heat will flow and heat will diffuse kind of in the material, okay? And so, yeah, just so it's written down, this last expression is what you get if you just write out this thing, okay? Okay. So the question is, well, how do we get to this equation, right? Well, the derivation is exactly the same as in one dimension, okay? So what we're interested in is, well, first, what is the rate of change of heat energy? Okay. Pick a region of space, take your material, compute the total amount of heat energy in there, and just take a time derivative. Right, how is that changing? Well, for us, there are just going to be two possibilities. One, we're either going to lose or gain heat energy by having heat flowing across the boundaries, say per unit time. So that's one possibility. The other possibility is to have kind of heat spontaneously generated or lost within the material per unit time, okay? And this is the exact same expression that we wrote in the one-dimensional case with the rod. Okay, so now let's try to figure out or write down what these pieces are mathematically. So before we do that, what might these regions look like? Well, here are a few examples. So R could be any sort of wonky blob in three-dimensional space, or your region R might be something like a cube, or it could be a sphere, or it could be a cylinder, okay? Generally, when we talk about these kinds of problems, in our minds, we might think of R as something like this, just some blob. In practice, when we actually go to compute things, R will be one of these, or something that we can actually write down in a nice way. But anyways, okay. So let's start writing down what these terms are. Okay. So what is the total heat energy? It's this expression. So recall, this is specific heat, mass density, temperature, and a volume element. And then we add up all of those volume elements. Okay. So this is thermal energy per mass per temperature. This is mass per density. Okay. This is temperature. So all of these together give us thermal energy per volume. Multiply by volume. In the end, we get thermal energy. Okay. And since we're integrating over all of R, we get the total thermal energy in that three-dimensional region R. Okay. So here I've written these as kind of these vectorial arguments. If you want, you can write everything out in terms of X, Y, and Z. But yeah. Okay, so that's the total heat energy. Question is, how does that change in time? Well, just take a time derivative. Okay, here I'm suppressing the arguments, but C and rho may still depend on space. And kind of, assuming our region is nice enough, assuming C, rho, and our temperature are all nice enough functions, we can move that derivative inside. C and rho only depend on the material and space, not on time. So this time derivative only affects temperature, okay? And so that's why we move it there and take that partial. Okay? So that's the rate of change of energy. And that's 1/3 of what we're looking for. Okay? So the second piece that we need to kind of write down is the heat flowing across the boundary per unit time. Okay? So what does that look like? Well, in the end, it's going to take this sort of expression, okay? This phi bar, this is going to be some vector field that's telling us how energy is flowing, okay? Here, so actually, okay, so let me go through these in order. So B here, that's going to be the boundary of our region. Okay? So we're looking over the entire boundary of the region, and we're looking at kind of how things are changing at that boundary. What are these other two pieces? So as I said, phi is this flux or how energy is flowing. Okay? And then this last term is this outward pointing normal. Okay. Yeah, so this term right here is just measuring, right, how much heat is actually leaving in the normal direction, or right, how much heat is leaving. And so I have some pictures of this. Okay, so suppose, right, this is our region R right here, and the flux will draw as a vector field, maybe like this, something like that. Okay, so just some notion of energy is flowing. And so what we want to do is we want to measure, right, this flux at the boundary. Okay, so what we're going to do is we're going to zoom in maybe on this little patch right here. Okay, and that's what drawn right here. Okay, so what is the flux out of this region? Well, maybe at this specific point right here, okay, the actual vector for the flux is pointing right there, whereas this is the normal. Okay. So if we decompose phi into its kind of normal component, right, the piece that's actually leaving, and the piece that's tangential to the surface, right, the only place that we're going to get energy leaving is from whatever component of phi, whatever that component, say, parallel to the normal is. Okay. Right, so what's a scalar that's quantifying how much flux there is at that point? Well, that's phi dot n, right? We have these two vectors. Right, and it's just the component of the flux that's normal to the surface. And so one point that I was getting at was, well, if the flux is parallel to the surface, right, or tangential to the surface, then we're actually not losing any energy, because kind of the energy is just getting shifted around in the surface. Okay? So kind of as a picture to illustrate that, right? Suppose kind of our surface is approximately flat. Here's the normal direction, but then the flux, right, is perpendicular to that, to the normal. Well, whatever heat energy is right here, whatever that concentration is, etc., we're just shifting energy over there, and we're not actually having any energy leave. Okay. So maybe this is further justification that, yes, what heat energy is lost or gained, it's whatever is kind of in the direction of that normal vector. Okay. So one comment about the sign, right? Well, we have two possibilities. Either phi flux dotted with the normal vector is positive, or it's negative. Okay. So what does it mean if phi dot the normal is positive? Okay. So since the normal vector is the outward pointing normal vector, right, pointing away from the interior, if phi and n point in the same direction, then we have energy that's leaving R, say. Right, that normal component is positive, so whatever the general flow is, there's some that's, say, tangential to the normal, that can be doing whatever. But then if we look at the normal component, it's positive, so it's flowing in the same direction as the normal vector, so it's leaving the region. Okay. Likewise, if phi and n, if phi dotted with n is negative, well, phi and this should be phi and n point in opposite directions. So energy is entering R. And so as an illustration of that, right, suppose that's our region. This is our normal vector. And then maybe phi is something like that. Okay, so then the normal component of phi is this, say with magnitude phi dotted with n. Okay. And so, yeah, in this way, we interpret this as, yes, there's flow into the surface because the vector associated with our flux phi and the normal vector are pointing opposite directions. Okay, and that's picked up because of this negative sign. Okay. Okay, so coming back, well then, what is the total energy flowing across the boundary? That's going to be negative this double integral over the boundary of the flux dotted with the normal vector over the surface. Okay. What's the interpretation of the sign? Well, let's see. So if the change in energy, in total energy, is negative, right? If we're losing energy, and there's no source that we have considered yet, then that means that the flux is sending energy out of the surface. Okay, so flux is sending energy out of the surface, phi dot n, that should be positive. Okay, but whatever flux we're losing across the boundary, that should be taken away from the total energy, right? So the change in energy should be minus this thing, since energy is leaving R. And that's where this minus sign is coming from. Otherwise, this is computing the total flux of the boundary. Okay, and then the last term, similar to what we had in the case of the one-dimensional system, is, well, just have some black box source term telling us how much energy is spontaneously added or removed from the system. So putting these all together, right, well, what is the rate of change of heat energy? That was this expression, I guess with the ddt outside. What is the heat flowing across the boundary per unit time? That's this term, right? Flux, the normal component of the flux per kind of area element, summing up over the boundary with the correct sign. And then finally, we're adding that source term. Okay. Which, again, is the exact same derivation we had in one dimension. Okay. So we're going to take, so the next part, what we'll do is similar steps, but we'll take this whole expression, tweak some things, rewrite some things, and then recover kind of, right, our original goal of what the heat equation, or the version of the heat equation in higher dimensions.